What's log? Okay, what's log? Okay, you know you have when we a plus b equals to something, if it's a reverse calculation, okay, a add something gives you this number. And now I want to work from this number back to a. I need to minus the number you just add. Okay, so it's a reverse calculation. Okay, a times a number, we get c. Okay, how we can work back from c to a? We need to go c divide by b to get back to a. So times and divide, they can be reverse calculations. So exponential and logarithm, they are reverse calculations. So what that means? A to the power of something gives you y. Okay, so a to the power of something gives you y. Okay, how I can calculate this power? Okay, so what I want to do is how I can calculate this power. So it's a to the power of something and then give you y. So if I want to calculate the power, it's not really add, subtract, times, or divide. So we need another calculation. So we know we have signs for plus, minus, and times we divide, but we don't really have a sign here, okay? Because we just write on the right corner, that means to the power of something. So same as if we want to go the reverse calculation, we don't have a sign. We introduce something called the log. So if I want to calculate x, we want to go back from a and y back to x. I need to go x equals to log a y. Okay, so a is at the bottom, it's like small number, and then y is on the same line as log. So it's log a y. Just be careful with the notation a little bit. You know, like we can have base a can be some number like 1, 2, 3, 4. Like I will talk about restrictions later. Let's say we can take numbers for a. You know, like e is also a number, like the nature number. We talk about e exponential, like the e to the power of x. That's a number as well. And when you write log ex, okay, log ey. So for example, if that's e to the power of x give you y, then x will be log ey. Okay, log ey. You must write the e at the corner, okay, like the bottom. You can't write on the same line of the log. Because when go to the meeting for when the exam assessor comes and they give us a meeting and they said they actually took marks off if your notation is incorrect. For example, a lot of students write log ex like this. And they said that's not log ex, that's log x. Okay, that's not log ex. So I don't know what's that. So you can't write that. So that's wrong. Okay, that's wrong. Like I know what you're trying to do, but that's wrong. So you can't do that way. So be careful with your notation. Okay, this is log. Okay, what is log? You can think about log as a reverse calculation for exponential. Okay, it's a reverse calculation for exponential. And now let's talk about all these restrictions. Let's have a think about this x. Okay, this x. Oh no, sorry, this a. I still make it back to a. Let's think about this a. What's the restriction for a? Do you still remember? Like when we talk about exponential, what's the restrictions of a? All positive except 1. Okay, what's the range for y? Like y equals to a to the power of x. What's the range? Do you remember the shape? All positive real numbers. So I will say 0 to infinity or r plus. Okay, so all real positive real numbers. 0 to infinity. That's my range. Now, let's have a think. This a, come here. Okay, this a is there. So in log, the base, this is still called the base of log. Okay, this is base of the exponential and it's also the base of the log. The base of the log needs to be a number r plus and not including 1. Why? Because of the exponential. Okay, the thing explained in exponential. So it should be r plus except 1. And what you can put in the bracket? is only 0 to infinity. That is the domain. Okay, what you can put in log in the bracket, that's only positive numbers because the range of the y, okay, see the y there, we can only get out positive numbers. You won't get negative numbers. So it's impossible to get negative from exponential, like a normal exponential. Now we only have domain 0 to infinity. So, well, like, if I swap my x and y, what I will have is y equals to log ax. This is the log function. Okay, this is the log function. They are inverse functions. Can you think about that? They are inverse functions. I just swap the x and the y and rearrange it. They are inverse functions. So log and exponential, they are inverse functions. Okay, so it's quite easy to understand. When I put x in, I get y. But when I put y into log, I should get the power. Okay, when I put the power in, I get the answer. When I put the answer into the log function, I should get out my power. So they are inverse functions. So exponential and log are inverse. And you need to be careful the a value. Okay, so again, restrictions for a needs to be all positive except 1. And all the x values needs to be positive. Okay, all the x values needs to be positive. So, well, you know, for year 10, I think we learned that in year 10. So last year when you learned this, normally, okay, like most of the time is you convert the log back to exponential and then think from the exponential and calculate. We can still do that, but it's too slow. Okay, but it's too slow. For example, I said, I just write the example here. Okay, so log 2(8). For example, I have this. I want to evaluate that. You will say, okay, I will make this number equals to x. This x must be the power. I can rewrite it into this way. Yeah, I can rewrite that into this way, and I know this x must be 3. So log 2(8) will be 3. Okay, log 2(8) will be 3. That's how year 10 teach you, like, what's the relationship between exponential and logarithm, and when you evaluate, what's the way, like, you will pick, like, you will make log back to exponential and easy to think about because it's more familiar. Okay, it's more familiar to you. But like year 11, we cannot just, well, we still can, but like it's too slow to use this method. Well, every time we have a long expression, every time we convert things back and we try to do calculations, that can be really slow. And sometimes it's not that easy to calculate this. So that's why we introduce all these laws, okay, all these laws. Just let you know, like all this proof, you don't need to know, you don't need to remember them. Like it's just for your interest. I'm not going to go through that in class. It's just for your interest. All of this proof, you can just have a look. And I want to tell you is, all of this formula is actually coming from exponential. Okay, if you really want to prove it, it's coming from exponential. So let's have a think about law 1. Okay, what you just need to remember from this page, how to use these laws. Okay, how to use these laws. So law 1 tells you log am, log a bracket m times n. If you times two numbers in log, that can be separated into two separate log, but you're adding them together. So for example, if I have log 2(8) times 16, I can say that's log 2(8) plus log 2(16). Okay, I can, well, I haven't tell you why I should do that. Like, there's a reason why we use this formula, but like that's the easiest example. You can see how we use it. But okay, students always forget where is times, where is plus. I see a lot of examples like this. They said that equals to log 2(8) plus 16. Do not copy that. That's wrong. Okay, it's like this is a common mistake. Times must be in the bracket and then you add it. But you times outside, that doesn't satisfy. Okay, so that's wrong. Okay, we don't have that one. So another really important thing is log has its own calculation rules, and all the rules you can use is listed here. Okay, every time you're trying to do some transformation or changing for logs, it must follow one of these rules. If you're just doing something from nowhere and you just think it's true, it will be definitely incorrect. Okay, everything you can do is on this page for log. Okay, you can't create calculation method by yourself. Okay, so that's the first thing we can do for log. Okay, the second thing you can guess for it already. When we have log A, m divided by n inside, we can have two separate log and minus it. Okay, and minus it. So it's log am minus log an. We can subtract it. Okay, so this is the second one, really important one we can use. This one is the worst one. Okay, this one is the worst one because I see students being really creative. They create so many things out. I just don't know where they're coming from that. Like they just think, oh, that's what I understand. Like it's really looks similar to normal calculation, like division calculation. So one of the worst thing I ever seen is, do not copy, okay? That's not another thing, not the supplementary thing. That's the worst thing I see. But do not copy, okay? That's wrong, yeah?
If you have log if you have log A and in brackets like
16 over 2, like that? Yeah, you can do that. But that's different. That's different case. What I'm talking about here is not the same thing. You can calculate the numbers. You can do anything to the numbers, like if the numbers connect together. But you can't create log. Like you can't create more logs. Okay, you can't increase the number of logs. Yeah? Yeah, you can. That you can do. You can do log A60 minus log A2. That's right. That's follow rule number 2. But like this one is incorrect, and I see so many students almost, okay, I'm not asking them to write the rule for me. I asked them to do a question, and the question is similar to the left hand side 4. You can see this question later. I give year 12 students this question and ask them to do because they already know their rules. And I see about like 2/3 of the class using the wrong rule. Well, they either use this one or another one. I can't remember the other one they used, but that's the worst thing. Okay, you're trying to create things for me. Like this is your creative formula, so do not create things. Okay, you can be creative, but not in log chapter. Okay, so that's the only thing we have. Okay, that's the only thing we have. Log am over n, that's log am minus log an. Okay, the third one. Third one is interesting. In the bracket, we have something to the power of something. We can drag the power into the front. So what that means, we have log 2 a to the power 4. I can say that's 4 times log 2 8. Okay, but this 4 must be in the bracket. Must be in the bracket. If you do this, that's different. Okay, that's different. That's not this rule. Okay, 4 must be in the bracket. This, if we do that, the power 4 means it's log 2 8 times log 2 8 times log 2 8 times log 2 8. So we can't use that formula. So you must have the 4 inside the bracket. Yeah. You can simplify that. No, it's power 4 of this number. So for example, this number is a 3. So it's 3 to the power 4 basically. Like log anything is a number. You don't need to think about like too much on it. It's possible. It's just a number to the power 4. Like if you can't evaluate, just leave it like that. If you have calculator, you can use calculator to evaluate. But overall, it's just a number to the power 4. There's not much meaning for it, but like that's the power then to the power 4. Okay, that's the third one. Well, the fourth one is the same as the third one. You can see. Okay, it's -1. We drag the -1 to the front. That's just minus log m. No difference between example 3. Okay, no difference between the log 3. So log 4, log 3, they're the same thing. Log 4 is a special form of log 3. Alright. Number 5 is important. There are two special values. That's how you solve x-intercept and y-intercept. That's the special value. Sometimes there's no y-intercept, but anyway, we'll talk about that later. But we have two special things for log. Log a1 must be 0 and log aa must be 1. Like say log b1, that's 0. Okay, log 2, that's 1. Why is like that? If we say log a1 equals to x, log a1 equals to x. So a to the power of x equals to 1. What do you think x must be? 0. A to the power of 0 is 1. And also your a is positive. Don't worry about the 0 case. So that's why log a1 must be 0. Okay, so another one is log aa. If we see log aa is y, a to the power of y equals to a. What do you think y must be? 1. Okay, log a to the power of 1 is a. So y must be 1. So that's why log aa equals to 1 and log a1 equals to 0. This one is easy to prove, but it's still through exponential. Okay, the proof is still through exponential. And we get these two special results. You can just cross out that one, like you don't need to worry about that. Okay, now I'll introduce two very important things. Very, very, very important things. Because in year 12, you use those two formulas a lot in the calculus chapter. You may not really use it this year, okay? So, but this is important for next year. And I don't think you will be taught that again. Or very briefly mention that. So one thing is a to the power of log am, that will be m. If you want to know why y is below, you can have a look by yourself. But okay, we'll give you an example. 3 to the power of log 3, 4. This number will be 4. Okay, 1/2 to the power of log 1/2, 3 over 4. That will be 3 over 4. Okay, it's just a formula. Just need to remember that. If you want to know why, you can see the proof below here. But I think it's quicker to just remember it. Okay, a to the power of log am, that is just m. Okay, that is just m. This is a very helpful formula in year 12. When you do some really special things, okay, this one is important. Okay, another use of this will be, I give you a number 5. And I said, I want to write this 5 into a number of base 4. Okay, I want to write this number 5 to a number with base 4. So what I should do is, that will be base 4 to the power of log 4, 5. That's how I can write the number 5. Okay, I can't explain why you need this, because it's year 12, like you need to do that. But when you see it, you will remember. Okay, I have talked about that in this lesson. So you can change a number to, well, you can say 5 is a base 5 to the power of 1. But now I want to change its base. I want to change the base to base 4. So we can go for 4 to the power of log 4, 5. Okay, you can do the backwards as well. Another important thing is change of base for log. Okay. Another story. Like, it's not really a story. Like, that's like many years ago, the calculator is not that powerful. We can't evaluate. Well, you have your calculator now, and if you want to type log, it will be control and this 10 to the power of x. You will have this log. You can put any base in. For example, I can say base 2 and of 8. And then I can say that's a 3. I can see directly evaluate for you, like that's a 3. Or I can find approximation values. For example, I change that to a 7. I can go control enter, give me 2.8 something. So I can evaluate anything now. But say like how many years ago, maybe 20 years ago, I can't remember what's the actual time. The calculator is not powerful enough, and they can only evaluate log with base 10. Okay, so they can do only base 10. The calculator only has base 10. Okay, only have base 10 something, base 10 something. You can only do everything for base 10. So now, for example, if you have a log 2.8, you don't know how to evaluate that. You want to use calculator, but you can't enter that into the calculator because you don't have base 2. What you need to do, you need to change the base. Okay, you need to change base 2 to a base 10. Or say if the calculator can work for base E, you need to change it to base E. If it can work for base 8, you need to change the number to base 8. So how we can change the base? So we change the base by using this formula. Originally I have this number with base A. And now I want to change it to a base C. But you can't just change to one base C. It needs to be base C divided by base C. So log AB equals to log CB over log CA. This C can be any positive number exclude 1. Okay, C can be any positive number exclude 1. C can be A or B. Okay, it doesn't say like it can't be A, it can't be B. So C can be anything satisfy log. You can still change it to base A, I can still change it to base B. It can be the same number as A and B. It's not going to be different, it's not necessary to be different numbers. So what that means? That means I also change log 3.5 into base 10, for example. I also change it to base 10. So that's log 10.5 over log 10.3. Okay, base at the bottom. Okay, the original base, that number become the number inserted log, but that's at the bottom. So it's log 10.5 over log 10.3. Again, you also know why the proof is below. You can have a look. That's still proof from exponential. Okay, still proof from exponential. Let's have a look at this. Log AB. Okay. I want to prove that equals to 1 over log BA. That's not something you can use directly. It's good to know, but like I need to prove it. How I can prove this? Okay, let's have a think about the number. On the left hand side, the number is with base A. On the right hand side, the number is with base B. Obviously, you can see there's a change of base happen. Otherwise, how A can become B, how I can swap it. So I will start from my left hand side. Log AB equals to what? Log AB. If I want to change it to any base, okay, it must be log over log. You can see I have changed it to base B. So that's log BB over log BA. And you can see log BB is a 1 because of the rules given above. So that's why log AB equals to 1 over log BA. I just do it by change of base. Okay, do it by change of base. example 1. Okay, now I will tell you why we introduce all of that. Okay, why we need to know all of these rules. Because I want to calculate things quickly. I want to reduce large number to small number and then easy for calculations. For example, the first one. What I can do is, that's log 381. 81 is a 3 to the power 4. Or you can say that's a 9 to the power 2. But I will make it to the smaller base. So that's 3 to the power 4. And then that's 4 times log 33. That's 4 times log 33. What's log 33? 1. So that's just a 4. That's why we don't need to use exponential to do calculations. I can remember the rule and directly evaluate that. Yeah, but like instead you write that equals to x and 3x equals to 81, 3x equals to 3 to the 4. Here? Here, yeah, like I'm just trying to show what's going on, like all the rules what we use. If you know it, like you won't have questions like that. That's too easy. That's just a starting, like what we introduce. Okay, you can see like the next page is actually the working you'll get, like the calculation you'll get. This is the introduce point. Like I want to make things slowly and then how to calculate. Okay. Second one. What do you make for inside? How you will change 1 over 27? 3 to the power of minus 3. And that's minus 3. Okay, minus 3 times log 33. 33 is 1. So that's minus 3. Alright, let's have a look at my favorite question. Okay, you try that first. You see what you can do. Give you a minute to think about. It's a number. Well, if you end up with a log, that means you do something wrong. And I think if you have log, you're trying to be creative. Some rules. You must follow some rule, okay? Must follow some rule. You just got look up. 1, 2, 3, 4, 5. Which one satisfied? Nothing satisfied? It's a number. And it's a nice number. It's not a really terrible number. It's a fraction. Yeah, it's a fraction. It's a fraction. You can't do that, okay? They are the same, no?
Same like log 2 times 5 and then log 2 times 7.
Oh, the log 2 can disappear because that's the same thing. Like they are the same number. Anyone give me a confident answer? Yeah, 2 over 3. Okay, so what we're trying to do here, okay, I'll just introduce first what my year 12 students do for me. They do log 349 over 343. That's the thing they do to me. And that's wrong. Okay, you don't need to copy that, that's wrong. So make it disappear and what we can do here is that's a log 3 7 over 7 to the power of 2, and then the bottom is log 3 7 to the power of 3. And then I can see that's 2 times log 3 7, and that's 3 times log 3 7. It's same as 2 times a over 3 times a. The a and a can cancel. This log can disappear. Like if you cancel exactly the same thing on top and bottom, but you can't cancel this. Okay, I see like one of my students doing that, and I'm so angry. Like why? You just make the log disappear. If you can do that, why I'm just asking you 49 over 343? That would be even easier. Which means we can't do that. Okay, and then she finally realized, oh, true. Oh, don't do that. Okay, so we have 2 over 3 in the end. Okay, everyone. So, what you need to do now is 1, 2, 1, 2, 3, 4, 5. Okay, so let's do 1 and 2 first, and then we compare answers, and then you do 1, 2, 3, and then finally 4 and 5. Okay, so do 1 and 2 first, give you 5 minutes, should be enough. Okay, for this one, a lot of you, like I'm very happy a lot of you recognize the 2 and then you can't combine with 1 of the log 10 16. So most of you put the 2 back into the bracket. So you do log 10 9 plus log 10 16 and then minus log 10 36 over 25. Okay, that's most of us doing. And that equals to log 10 9 times 16 divided by 36 over 25. Yeah, that's what we do. After all the calculations, you have log 10 100. And you know that's 2 log 10 10. That's 2. But there's another way we can do. We have the 2 in both, like we have 3 terms. 2 terms contain the 2, right? We can make the third term contains the 2 as well. So I'll make this stay, and I'll make a 2 log 10 4 for this one. And I'll minus 2 log 10 6 over 5. So 2 will be a common factor. 2 will be a common factor. So I have log 10, 3 times 4 divided by 6 over 5. And that's 2 log 10, 10. And that's 2 as well. This is easier calculation. Okay, it's just an easier calculation. Both methods correct, they're all good. I just think if you get the 2 out, it's reduce all the numbers. I want to calculate small numbers instead of larger numbers. So that's what I will do. For this one, okay, when we're not familiar with it, we're still trying to divide those 2. Like, even though you not write it together, you can't calculate 2 logs bracket. Okay, you can't calculate like the bracket separately. You need to consider the log together. So what we can do here is a 3 over 2 times log 6x over, that's x to the power of a half. So that's a half times log 6 to the power of 6x. Okay, we get the 2 power down. And these 2 can get cancelled. We just have 3. Okay, we just have 3. It's the same as the previous question, like in the both page. All right, that's example 2. Any questions for those two? If no, well, I see most of us finish this 3 as well. I also save some time for the last one. The last one is important. So I can just solve this one with you together. Okay, this is log, remember yesterday we do exponential equations and exponential inequalities. We have log equations as well. So all the log equations will be solved by exponential. So we need to convert everything back to exponential. Or what we can do is, well, for example, this one. X to the power 4 equals to 256. Okay, there are 2 ways to do it. Let's have a look at what's 256. 256 divided by 4. 64. So 4 times 16 times 4. And that's 4 times 4 to the power 4. So what I would do is, that's log x 4 to the power 4 equals to 4. Okay, 256, I make it 4 to the power 4. And then we have 4 times log x 4 equals to 4. So log x 4 equals to 1. Then x must be 4. I'll say why I'm doing this. Okay, I'll say why I'm doing this. I'll go for another way. Yeah? Oh no. Okay, that's one way of doing it. I get the 256 to 4 to the power 4, drag the 4 out, cancel with the 4 on the right hand side, become a 1. So log a equals to 1. I can use that rule to get x equals to 4. Another way I think most of us will do is x to the power 4 equals to 256. Okay, x to the power 4 equals to 4 to the power 4. What x can be? According to what you write, is plus minus 4. It's an even power. Like x will be what? X will be plus minus 4th root of 4 to the power 4. So x will be plus minus 4, not only 4. No, the answer should be 4. But according to your working, the x can be negative 4 as well. Because negative 4 to the power 4 is still 256. Nothing wrong with it. But you will say, because x can only belongs to R positive, exclude 1, so x equals to 4. You need a bit discussion here, because it's the restrictions for log. Okay, log got restrictions on both of the base and the number in the bracket. They all needs to be positive. Okay, if you use the left hand side, no problem. Easy answer, 4. If you use right hand side, you need the discussion there. It's not just 4. It can be minus 4 when you have the third, the second last step, and then make discussion. When you take even root, you must have plus minus in front. Like x to the power of even root, that is plus minus of the root of that even number. Okay, plus minus of the even root of that number. Any questions? No? Okay, next one. Well, next one is easy. X equals to 5 to the power of a half, and x is root 5. Done. That one's easy. Why not? Why we confused? It's fine? Okay. Okay, this one. Instead of put the 3 into the bracket, you can just treat as 3 times something equals to 12. And you know that log 2x must be 4. Okay, 3 times 4 equals to 12. You simplify first. Okay, do not increase the number. Okay, do not increase the number. So what we have is x equals to 2 to the power 4 and x is 16. X is 16. Okay, it's easy to solve for log functions. You just get things back to exponential to do. Let's have a look at the next two. The next two is the important thing. Okay, I'll do 4 with you and you do 5 by yourself. Okay, for this one, log 2 2x plus 1 minus log 2x minus 1. What I will have is log 2 2x plus 1 divided by x minus 1. When you subtract to log, you can divide them. And when you subtract to log, you can divide them. So 2x plus 1 over x minus 1. That's 2 to the power 4. Still write it back to exponential. Okay, 2 is the base, 4 is the power, equals to the thing in the bracket. So 2x plus 1 equals to 16 times x minus 1. 2 to the power 4 is a 16, and we times the denominator to that side, like say on both sides. So 2x plus 1 equals to 16x minus 16. So 17 equals to 14x, and x is 17 over 14. X is 17 over 14. All right. If you don't have any questions, can you try the last example? Okay, try the last example. Give you 5 minutes. Okay, give you 5 minutes. I can only give you 5. We only have 10 minutes left. So 5 minutes you go through, 5 minutes I explain. It's very important. Okay, I must go through the last one. So I will start at 10 past 12. Okay, we have this, and everyone have done this step, like it's x minus 1 times x plus 1, and that equals to 1. So x minus 1, x plus 1, that equals to 3 to the power of 1. That's x squared minus 1 equals to 3. And x squared equals to 4. And we have x equals to plus minus 2. Okay, we all up to here. And then we think, negative 2 doesn't look right, because x can't be negative. No, that's not the reason. It's not always x can't be negative. Why? What I need is the thing in the bracket to be positive, not the x to be positive. Okay, so what I need is x minus 1 to be greater than 0 and x plus 1 to be greater than 0, not the x. Okay, it's nothing to do with the x. Nothing to do with the single x. It's the whole thing in the bracket must be positive. So my x will be greater than 1 and max should be greater than that. I need an and. Okay, it's an and relationship. I need that to be greater than 0 and that greater than 0. So we have minus 1, we have 1. Okay, greater than 0, greater than that. So overall, okay, my x domain should be 1 to infinity. Okay, 1 to infinity. That will be the domain for this question. Okay, I must have things 1 above. It's not strong enough. You just say it's 0 above. For example, if it's half, that doesn't work still. Okay, still not true. Well, that's the thing I said. Sometimes can be both satisfied if both numbers can make the thing become positive. Sometimes it can be both wrong because both numbers up in that all give you negative. So that depends. Okay, that depends. So because my x needs to belong to 1 to infinity, that is my domain of this function. So my x can only take 2. That should be your explanation. Or I can say, when I sub x equals to negative 2 into both functions, I have a negative domain. So that's why it doesn't work. You can also explain in that way. Questions? Okay, done for today. Tomorrow we'll go for next page.